Hello everyone, this is Masataro Asai from IBM Research. Today I talk about a negative but still interesting results on learning a descriptive action model from images. We all know that planners can solve an image puzzle optimally in a fraction of a second, but only when we have a PDDL model. They cannot solve an image-based puzzle because we do not have a PDDL model. LatPlan, however, is a system that can solve such a problem without any prior explicit knowledge given by human, such as this image contains 9 tiles or that these tiles could move. LatPlan has two inputs. The first one is the state transition dataset that trains this system. It contains an unknown high-level action between the states. The second input is an initial image and an or image which specifies the planning problem. The output is a visualized plan. Latent-Space Planner architecture contains a domain-independent classical planner at its core, which requires PDDL. However, all the inputs and outputs are in the subsymbolic raw representation. Therefore, we need to bridge the gap. The first step of LatPlan performs this by training a neural network called State AutoEncoder, which provides a bidirectional mapping between images and the propositional states. The states are fixed size bit vectors, which can be seen as a propositional assignments. The next step is the action model acquisition, which learns action model from the propositional state transitions produced by the state autoencoder. From the action model and the initial states and goal state, we can produce a plan using a domain-independent classical planner. We can simulate the plan to obtain the intermediate states, which are not made for humans, so needs to be decoded back to the visualized image to understand for humans. AutoEncoder is an unsupervised training method for the neural network. It tries to perform lossless compression by targeting an identity function. It consists of two parts, the encoder and a decoder, where the former maps the input to a smaller latent vector and the latter maps the latent vector back to the input. The training is performed by minimizing the difference between the input and the output, which is called the reconstruction loss or error. These latent vector z is real valued, so useless for the propositional logic reasoning. These days, however, there are several discrete autoencoding methods that are available. The 6 examples I showed in this slide all provide the categorical variables that are directly compatible with symbolic systems. We use Gumbel softmax and binary concrete. However, the only difference between these is the training stability and performance. State autoencoder after the training contains a discrete binary latent space and then reconstruct the same input. Action model acquisition, that's in the step 2, consists of two neural networks, action autoencoder and action discriminator. AAE jointly learns the enumerable action labels A, as well as how to generate a successor for A. In other words, it learns how to change the state, therefore the effects. The action labels are learned unsupervised and is not included in the dataset. Note that not all actions are applicable to the current state. It could result in a duplicated tiles or swapping 3 times at once. These incorrect transitions need to be pruned during the search. Therefore, we train an additional neural network called action discriminator, which are binary classifier. The training detail is omitted due to the time constraint. LatPlan lacks evaluation on truly difficult combinatorial tasks. 8 puzzle is easier than the 15 puzzle. In order to scale LatPlan to such a more difficult combinatorial problems, we need to combine it with a good domain-independent heuristics. It needs to be domain-independent because our domains are generated by the neural networks. An issue is LatPlan AMA2 is not able to produce PDDL. Therefore, the state-of-the-art heuristics is not available. Previously, we addressed this by building a custom planner that uses a call count heuristics, but this is not ideal. In order to use the state-of-the-art heuristics, we need the descriptive action models, not the black box action model. To address the issue, we propose double-stage AMA, which, after the training of the initial neural network training, additionally trains a decision tree algorithm, which are then converted into a logical formula, which will be used inside the PDDL domain definition. We compile decision trees and random forests as follows. Decision trees consist of multiple decision nodes and the leaf node. Decision node has a threshold value and the array index. So this case, 0.7 and 3, is looking at the third proposition and telling whether the value 1 is larger than 0.7, which is the case, therefore it goes to the right branch. The leaf node contains a class probability vector corresponding to the true and false. The logical formula is created by the equivalence between the if-then-else rule and the certain logical formula. DSAMA models the effect as follows. The random forest predicts each bit from the entire current state. After the training, we convert each random forest into a logical formula, then establish two conditional effects, one for the positive case and another for the negative case. For the negative case, we use delete effects. The preconditions are straightforward, so I omit the description. Here is the experimental results of the effect modeling accuracy. We observed that the random forest achieves almost comparable results as the neural network. In the precondition learning, we sometimes even observed that the random forest outperforms the neural networks. But here's the problem. Our PDDL compilation is so large that fast downward fails to start the search before the time runs out. Moreover, if we try to make the model smaller by restricting the hyperparameter for the random forest, then the model becomes less accurate. Even if we use the small and inaccurate problem instances, it causes an exponentially large compilation. This is because fast or downward uses disjunction flattening. This is a technique which moves the disjunctions upward and then make a duplicate copy for each branch of the disjunction. This causes a memory exhaustion, especially because our model contains lots of disjunction in each of the conditional effect. So here's the conclusion. We found that our effect and the preconditions are quite accurate, but the result is useless. We hypothesized that the reason of this is the propositional representation that is already learned and dumped into a file by SAE could be arbitrarily complex. Therefore, there's no guarantee that there's a compact model that describes it. While a neural network and the random forest are so powerful that it can still learn from it, the logical translation is too complex for the fast downward. Our Ichikai 2020 paper addressed this by restricting the state transitions during the training of the SAE. However, there are two more potential directions to address this issue. The first one is a planner that natively supports the disjunctions, and the second one is a novelty-based planning that does not use the action model. What do you think is the best future direction for this line of work? Please leave the comment in the discussion chat window. Thank you for listening.